Okay, so today we're going to start our next chapter, which is chapter 6. And I do want you to read this chapter really well. If you look in the chapter, it's got very good examples. And don't skip over those. I mean, you have to step through the examples that it gives you. So you especially want to read through and, don't forget to go through the problems and the examples of how to work them. Okay? But we're going to start it today and get you a good idea of what's going on with that chapter. I also would say, we're going to work some of this worksheet together, do that in a game fashion, and then there's 5 problems for you guys to do out of your book. That is written at the bottom of your worksheet, by the way. So, okay. I was thinking, this is a lot of stuff, and so I would allow you to maybe break this chapter up over the next couple of days. We're having 3 class periods on one chapter. So if you wanted to break the reading of this chapter up, you can. It would, of course, benefit you to read it all this weekend, but, I know we got stuff going on. But break it up and just read it as quickly as you can, because the quicker you read it, the better you'll benefit with the other stuff you're doing. Okay. Let's see. Did we get all our stuff? Remind me to stamp you for your note cards at the end of class. I want to get going on this. So here we go. Okay, you got formula sheets. One of them is your descriptive statistics and probability. And the 2 formulas that we know on that are the X bar, what's X bar mean? And then we also learned S, which was, and sometimes it's sigma, because that would be when it's over the entire population, okay? So we know those 2. And then you got 2 other papers that look very, very similar to each other. Please pull those out and study them. One of them is a Z-score table. One of them is a T-score, and I think it has P on the back. So you need to be aware that there are tables that look alike, and so make sure that when you are getting your information, you're on the right table. Don't you think that makes sense? You want to make sure you're getting it from the right one, and so they look alike. And I wanted to point that out to you because on the AP test, they'll be right there next to each other also. So you need to know that there are ones that look alike. You want to use the correct one. We are going to use the Z-score table today and learn what all that means and how that looks. All right? So let's do notes to kind of get an idea of what's going on with this chapter. On standard deviation, which we've already addressed in chapter 5, and the normal model. Okay, so you guys have your notes, and let's do that. Here we go. All right, standard deviation, remember, that's telling us about how far the typical distance is away from the mean. So standard deviation is a measure of spread because it tells us how much the information varies, or the variability is the word here, from the mean. The smaller the deviation, what do you think that means? The closer things are to the mean and the smaller the deviation that things are away from the mean, then what's happening? We have less variability in the data. When we had our test, if the standard deviation was small, then most of the scores were centered around the average, pretty close to the average. The larger the standard deviation, the more variability we have. So if we had a standard deviation of 14, I think that's pretty significant. That means, there's a pretty big spread because the typical data is 14 on either side away from the mean. That make sense? Questions there? Okay, standard deviation can be a ruler for measuring how individuals' values compare to a group. To measure how far above or below the mean any given data value is, we find its standardized value or its Z-score. So let me tell you a little story, though, first. And you're going to read it. This is really good. I loved it. It was in the first part of your book in the chapter. And it was a story about in the Olympics, and, they were bidding for the Olympics, wasn't Obama trying to get it to be brought to Chicago. But it talked about the Heptathlon. Okay? So in the heptathlon, you have all these different events, right? How many different events would you have? Okay, good. You have 7 events. So, let's say that one person does really, really well in a javelin throw, and she wins, and then she does pretty okay in the high jump, but she doesn't win that. I mean, how do we compare your scores to a javelin throw, to a high jump, and how well you did? How do you then come up with an overall average of all these different events that have different scoring methods? So you understand why we would then need to have a standardized score. So if we had a standardized score and we said, okay, for this event, all of the participants averaged this score, particular score, and then we see how far you deviate from that average. So that's how you get a standardized value. That will be your z-score, and that is that's your standard deviation, how far you deviated from that average. Okay, so here we go. To standardize a value, we're going to subtract the mean and divide by the standard deviation. You would have to memorize this. So this is z equals, and you might see it on your formula chart as x, or no, it's not even on your formula chart, so you have to memorize it. X minus x bar. So that's how far you are away from the mean, and then divide it by the standard deviation. So we're going to do that. We're going to use my measurements here so we're all the same, because it says measure your inches in height, your height. Okay, so I am 5'8", so how many inches am I? So I'm 68 inches, okay. So right here, we're going to use Miss McClellan's information. And so Miss McClellan is 5'8", and so I'm 68 inches tall. All right. And so it says, calculate the standardized value. So let me compare myself to the standard and see how far I am off from the standard. So calculate the standardized, or given that the average is 64.5 inches for women and the standard deviation, so the typical woman deviates from that average by 2.5 inches. So how tall am I? Am I tall? I'm 68 inches tall. How do I relate to the average information? How can I find my standardized score, how far I deviate from everything? Good. Take mine. Very good. Which is 68 minus the mean, which is 64.5. And what am I going to divide by to standardize it? Divide by the standard deviation, which it tells me is 2.5. Okay? If you calculated that, that is 1.4. So I am 1.4 standard deviations above the average height of women. So am I taller than average? Yeah, okay. And so then we're going to also now, I want you to relate it to your table, and I'm going to show you how to, I don't have a table up here on the board here, and I should have. Man, that was, okay, I'll have to put that in there. But let me show you how to relate that now to your Z table. So let's go to your Z table, and let's see how many women I actually am taller than. Okay, so if you go to your Z table, and I'm going to write it here so it's on the recording, your Z table is telling you the chance that you, so if this is the mean, and then this is one standard deviation away, where would I be? If this is one standard deviation, I'd be over here at, you know, I'm 1.4 Z-scores away. So I'm further than one standard deviation away. So I'm taller, and it's always the area under this normal-looking curve from our histograms. This is, remember how we talked about being normal and being symmetrical is giving us really close mean to the median? And so this Z-score gives me so I am taller than all of these people that fall into that category. So if I am 1.4 standard deviations above average, I'm taller than all of these people. Good. So let's find out what that is on our Z table. So go to your Z table, and it kind of looks like this. And you need to find over here in this column the one that says 1.0, positive. So look for the positive one because I'm above the mean. Do you notice on the front page it's below them? It's the negative. That's below the mean. But I'm on the positive side, so look on the back of your table. And then look at these here. See how this is 0, 0, and or 0.00, 0.01, 0.02, 0.04. But actually, I need to be down. If I'm 1.4, isn't there a one that says 1.4? Okay, so I need to be down at 1.4. And did I have any decimals after my thing? No, I was even 1.4. So I would be 1.400. So I would be whatever this number is right here. 0.9192. Okay, so you follow that? So you know what that means? I am taller than how many people? 91.92% of people. So I'm taller than 91.92% of people. See, I took that number and I turned it into a percent. Of women. I'm taller than 91.92% of women. Yes. Well, and I'm not, is this correct? I don't know. That's just put in there. On average, no, I don't know. That's what, if our population is normally distributed, which we should be because as you get more and more things going, yeah, okay. What do you think about that? Okay, so let's talk about shoe size. Suppose the average woman's shoe size is 8.25 with a standard deviation of 1.15, and the average male has that. Okay, do you have big feet? Oh, do you have big feet? Well, we're doing mine again, so we're all doing the same thing. I wear a size. I go get my New Balance at the New Balance store, and I put my ideal feet insert in them because I have plantar fits, So anyway, so I got myself a 9.5 size foot. So I'm 9.5. So put down there, Miss McClellan's 9.5. Let's do that. So Miss McClellan is a 9.5. Okay, so what's my Z-score? How far am I away from average? Well, how do I do that? Mine minus the average, but standardize it by dividing by the standard deviation, which is 1.15. Okay, so how far away am I? 1.09. So that's interesting. How does that relate to how far my height was? Does it coincide? Am I the same? Are my feet bigger than 91.92% of the population as well? No. So my feet are not quite as big as my height in comparison in a standardization. See? So I'm relating my shoe size to my height and seeing if I'm equal in those comparisons. So really my foot is a little smaller in relationship to my height than standard. So think about what this is going to look like. If this is the mean, if the mean's right here, and I'm 1.09, I'm about one standard deviation above, so I'm just right here on this line here. But you see, I'm taller than all of these people over here. That's the area below me. So how do you find that on your Z chart? Go find it, go to 1, and then what do I do? Okay, I need to go all the way over here to 0.09. And what is that value right there, 1.09? 0.8621. 0.8621. So y'all looked it up? So my feet are bigger than 86.21% of women. Good? Follow? Excellent. Okay, let's go on. We're going to skip Sharon and Andrew. Okay, here we go. In order to compare the values that are measured using different scales, because see, my height is different scale than my shoe size, we had to first standardize those values. Standardized values have no units. So that 1.09, that was the standard deviation. That is not a measurement. That's a standardized score. If the value is above the mean, what was it? Remember? If it's above the mean, then it's a positive score. If I'm below the mean, then my z-score is a negative score. Okay, you can follow that because we've kind of been talking about that already. Okay, so what would a z-score of 1 mean? You are what? 1 standard deviation above the mean. If you had a z-score of negative 0.5, what would that mean? You are a half of a standard deviation, 1/2 of a standard deviation below average. Okay? Questions there? Follow that? Follow how to read that on your z-chart? All right. So the larger the z-score, the more unusual it is. Okay? Because with a standard normal, if we're looking like this, here's 1 standard deviation, here's 2 standard deviations. Look out here. Here at 3, I mean, look at that. Once you get out there to 3 standard deviations, is there very many data out there? I mean, this is just not very many people, is it? This is a whole lot of people. This is most people right here. Think of like histograms. Okay, this is most people. Then we're getting less people that had that height, and less people and less people and less people, and not very many people at all right here. Okay, so that'd be interesting to see, like some of you that are tall, what your percentage was, even taller than me. Okay, good. Next. We're not going to deal with this page really too much. We're going to skip over this, but I will tell you this. If you add something, that is shifting it back, adding a constant. So if I say I need to add $50 to across the board to the entire salaries of Aledo ISD, then if our normal, see this right here is the average teacher's salary. If I added $50 across the board to the entire teacher's salary, what would it do to my normal curve here? If I added $50 to every teacher's salary, it would take this thing and then it would just do what with it? Shift it 50. Okay? So adding just adds 50 across the board. It just shifts it, and did it change the distance from here to here? Did it change the spread? How far the highest was from the lowest? No. But did it change the average? Yes. It affected the center. So if I add, it would affect the center, but it would not change doesn't affect the spread. So it affects where the center is, but it does not affect the distance from the highest to the lowest. Okay? Questions there? If I multiplied by something, okay, let's say this is a normal. Remember like when we did AH and K and all that stuff in Algebra 2? If I multiplied by a constant, then you know what that would do? I believe, depending on what the constant is, we would get something like this. Oh, that was supposed to be normal still looking, but steeper. The constant makes it steeper. So it should actually affect where the center is. It should actually kind of affect everything. So if I'm multiplying, it's doing that. So it should affect where the center is. And what else does it affect? The distance from the highest to the lowest. So if you multiply by something, it will affect the center, and it affects the spread. And that is not incredibly, hugely important. I mean, because you can kind of figure that out as you just plug through some things. And so I'm not going to do any further into that. All right. We are going to be experts in this thing called the normal model. That's the whole thing, this chapter, and a lot of the rest of the year is based on, okay? Super important right here. The normal model is symmetric, it is bell-shaped, and it follows a very important rule. So I'm going to draw it right here. but you have it on your next page. 68% fall within 1 standard deviation of the mean. If there's the mean, and here's 1 standard deviation, and here's minus 1 standard deviation. So here's the average height. 68% of women fall within 1 standard deviation of the average. Let's go back to that example previously. Let's talk about average women's heights. What's the average women's height, did it say? 64.5. What was the standard deviation? Didn't it say 2.5? Okay, so how tall is this person that's 1 standard deviation away? Add 2.5, that would make it, how tall is this person? So this person's 67 inches. How tall is the person that's 1 standard deviation shorter than the mean? 62, okay. So guess what? This normal model says that 68% of women are between 62 inches and 67 inches tall. 68% of women are in between 62 inches and 67 inches tall. Okay? These numbers, 68, that's like a... okay. I added a standard deviation, which it told me on the first page was 2.5. And then I subtracted a standard deviation to get here. Okay? Good question. Good question. You follow that? Okay. Let's see. So let me ask you this. How many women, what percentage of women are between 64.5 inches and 67 inches? What percentage of women? Yes, very good. 34% of women fall in right here. Okay, good. All right, and then you can say 2 standard deviations. So how would I get to 2 standard deviations out here? I would have added 5 or add another 2.5. And what does that get me up to? That's 69.5, okay. And then what's minus 2 standard deviations here? Subtract another 2.5, and what does that get me to? 59.5, okay. So according to this information right here, how many women are between the heights of 59.5 inches and 69.5 inches? 95. I would have to say that that's correct. So 95% of women are between 59.5 inches and 69.5 inches. Okay? And then as you get out here to 3 sigma, I would add another, you get the picture? I would add another 2.5 inches here. Go ahead. Right here. 68 fall within 1 standard deviation. 95% fall within 2 standard deviations. Yes. If they don't give you the standard deviation and stuff, then you know you would maybe calculate that from a sample. Okay, good. Okay, so look at your page. You have this. Instead of me writing a whole bunch of stuff on there, then let's take a look. This is, do you see? So here's the mean. 68 fall, 1 standard deviation above and 1 standard deviation, okay? And then here's to 2 standard deviations and minus 2 standard deviations. Got that? And then 99.7% fall out to 3 standard deviations. Okay. Following that? All right. When we divided by the standard deviation, like when we divided by 2.5 and we got me a z-score, when we got me a z-score, you know what that did? It create, you know what? I think you can understand this. Look here. Whenever, I was 68 inches, right? So, you know, I was 68 inches. Let's see here. No, here's how it is. Okay, you ready? the average women are 64.5 inches tall. So let's say this is 0, and you don't have to do this, but just watch this demonstration. Here's what's happening. Here's 64.5 inches right here. That's the average women's height, right? 64.5 inches tall. Okay? And look at how tall it is. It's 2.5 times. It's huge. It's 2.5 times bigger than this. It's supposed to be. To get a Z-score, I take the, if I want to make this go to 0, what should I do? If I want to make 64.5 go down to 0, what should I do? I should subtract 64.5. Very good. So if I want to make my mean 0, I should take my mean and subtract its value. So I shifted it down here to 0. If I wanted my standard deviation to be 1, what should I divide by to get this shortened down to just a standard deviation of 1? I should divide by the standard deviation. That's how that formula comes about. Because they take the model, they subtract it over there to 0, and then they divide it by the standard deviation to shorten it and get it to a standard deviation of 1. That's abstract. That's where the formula comes from. If you followed that, you're good. Not necessary, but that's what's happening. Okay, now if we were talking about the perfect normal model, you know how you asked me on the calculator, do I use SX or do I use the sigma X? Remember that? We didn't know? We were dealing with samples. So which standard deviation did we use? SX. But guess what? Since the normal model is determined and it is a model, it's supposed to represent the entire population. So if we're assuming a normal model, then that represents the entire population, and we use the Greek letters. Mu, so write this in here, there's a mu. Mu would be the mean, and sigma would represent the standard deviation. So again, I've been writing it kind of along. There's 1 standard deviation, there's 2 standard deviations, there's 3 standard deviations, and so on, and it keeps going. Sigma and mu. Yep, it says sigma and mu. Mu stands for the mean. Yeah, if I was talking about the average height of men, then their mu is something different.
No, I mean like different.
Oh, I don't think so. So in physics, it's something else. I'll have to get with her and talk to her about that. Okay, I'll ask her. Okay, no, I'll talk to Miss McCain and talk to her about that and see what that is. Okay, we talk a lot. We converse, and because it's all right. What would be over here on the left-hand side?
Negative.
-1 sigma, -2 sigma, -3 sigma. So label your normal model. Okay, good. Next page. I'm sorry, what? Does the sigma have what? 2 signs. Oh, if I was a short person and I was below the mean, then my standard deviation would have been over here on the negative side. And I would have been only taller than, you know, if I was 1 standard deviation, I was 2.5 shorter than average, then I would have been taller than this much people. And my standard deviation would have been -1. Okay? Does that make sense? Okay. All right. This kind of goes along with what I was saying, the development of the formula. The larger the sigma, the more spread out it is. So if we had a sigma that was 2.5, that's going to be a nice, taller looking model, as opposed to if I had a standard deviation that was 14, that's going to be much more spread out because our data is going to go further spread out. All right. So you can write that. The larger sigma, the more spread out the normal model appears. The inflection points occur a distance of sigma on either side of mu. Sigma on either side of mu, that's here and here. Okay. a standardized normal curve, subtract the mu, and divide by the standard deviation. So for the whole population, we would say Z is your data, whatever it is, X minus mu divided by sigma. Because now we're talking population values, the whole parameter as opposed to sample. What's it called with a sample? Just a statistic as opposed to the whole population. Okay. Finally, there's some stuff in your book about assessing whether something is considered normal, and you could put the data into your calculator, into your lists, and if you did this, in fact, when you go to your book, we're not doing this part of the lesson today, but you can go to your book, and there's something on this about the normal model, the normal plot. And it takes it through, it has something in it about it in your calculator. So read that. I did it yesterday. It has a really nice little short amount of data. You put your data into your list, and then you go plot it, and it step by step tells you how to do that. And if your plot looks about linear, then it's a normal distribution, and you could then use all your normal model rules. And the normal model rules are that we want to say we've got 68, 95, and 99.7. See, look at this bottom one. See how it kind of looks curved? It almost looks parabolic as opposed to linear. And so this bottom one would be considered a skewed distribution, and you would not want to use all your normal model rules with it. But this one that's nearly normal, then we go, oh, yes. I have something that's nearly normal. Excellent. I can use all my normal information. All right. Now, I think we get to play our game now. Yay. Okay, this is Jeopardy. So, yes, we are going to get into groups. Oh, I was going to have y'all get into your separate groups, but I will let, do you want to stay in, I don't know. Do you want to stay in your group tables? Let's stay in your groups. And I'm going to put y'all two with them over there. Okay. So that's perfect. Now we're all groups of 4, and we're going to be in groups, and the winning team gets 3 stamps. And furthermore, we're going to do part of your normal distribution page. That's homework. So we're going to see how to do this stuff. All right, so you need a calculator if you do not have that. And I'll come on and I'll show you guys some of these answers in a minute. So get your calculator and get set. Otherwise, you're just going ahead and doing these problems.